Hello and welcome to this video for C108 Mechanics of Deformable Solids. We are still in chapter 4 on axial load problems. In the previous video, what we saw is how to define and how to calculate the internal load, what is the sign convention, the positive sign convention to use, and how once you have the internal load, you can calculate the internal stress. So this is going to tell us about the risk of fracture within a beam that is subjected to some axial load. Now what we are going to do is to talk about the elongation. So how to calculate the actual elongation, the change in the length of a beam that is subjected to some axial load. So here what we are going to derive is a general formula that can work for an arbitrary beam with an arbitrary shape made of an arbitrary material and subjected to some arbitrary load. So we need to consider a very general case, the most generic possible, and derive the formula that's going to give us a way to calculate the actual elongation of a beam that is subjected to one or several axial load. So for this, let's consider the general case like this. When you have a beam that is going along a given axis x, and so we are going to define this beam, for example, like this. We are going to consider that this beam can have an arbitrary cross-section that can change as a function of x. So if this beam goes between 0 and L, for each x, you will have a given cross-section, which can depend on x. And also at each x, so the beam can be made of different materials, and each material can have a different Young's modulus. So the Young's modulus can also potentially depend on x. So then this beam is going to be subjected to one or several load. So you will have a series of load that will be applied, and due to the load, this beam is going to be deformed, which means that if initially the beam is going between 0 and L, so this is the beam before deformation. In this case, L would be the initial length of the beam before any deformation. After deformation, after the load is applied, this beam can be either compressed or elongated. So for example, here, we would have something like this, where the beam becomes elongated like this due to the application. So in this case, this would be after the deformation of the beam due to the application of the external load. And so what we want to calculate specifically here is this. We want to calculate the elongation. So if the beam was initially going from point A to point B, we want to calculate the elongation of the beam between point A and point B. That is to say, the difference between the new distance between point A and point B, that is to say the new length of the beam, minus the former distance between A and B, so the former length of the beam. So we want to calculate the change in the length of the beam after, with respect to before deformation. This is going to give us the elongation in the same way that we define the elongation in the strain, the chapter on strain, where in this case, the notation that we will be using, the elongation should always be defined between 2 points. So in this case, this would be the elongation between A and B. So to define the elongation, it needs to be a change in length. So we need to define between which point this length is initially defined, and what will be the change between the distance between those 2 points. So we always need to define 2 points like this when we define an elongation. So in this case, the goal of this is how to calculate this elongation for an arbitrary beam, arbitrary shape, arbitrary Young's modulus, arbitrary load. How do we get the elongation of this beam? So for this, since the cross-section of the beam and the load and the Young's modulus can potentially depend on any point x within this beam, what we need to do is to isolate a small section of this beam. Why? Because if we isolate a very small section of this beam, and what we are going to do is to isolate an infinitesimal section between x and x plus dx, where x is very small. If we choose dx to be very small, then we isolate an infinitesimal section of this beam with a very small width, an infinitesimally small width, And if this width is very small, then we can consider that within this small width, then the properties of the beam will be constant. If dx is very small, then between x and dx, the cross-section A, the Young's modulus, and the internal load will all be constant. And this is only because we choose dx very small. So what we are going to do is to isolate a small cross-section of the beam going between x and x plus dx. And then we are going to look at specifically this section of the beam and apply the condition of equilibrium to this beam. So let's do this. So let's take this beam. So we are going to isolate an infinitesimal portion of this beam. And so infinitesimal portion of this beam, between x and x plus dx. So we go between x and x plus dx. And again, we choose dx as being very small so that this beam is infinitely small. So if we draw this beam, so now we have this small section of this beam. It goes between x and x plus dx. So since this beam is very small, we can consider that the internal load will not change between x and x plus dx. So we choose a beam that is so small that we can consider that the internal load is going to be constant. So in this case, so we will have the same internal load on the left and on the right. And in this case, we will define the internal load with the positive sign convention, that is to say, always pointing towards the outside. So now, because of the deformation, because of the load that is applied, this beam is going to be deformed. So you will have a small deformation of this beam. So you will have a small elongation, and this small elongation, because it's a very small elongation, so it's an elongation, so we are going to write it delta. But since it's a very small elongation between only x and x plus dx, we are going to write it d delta to indicate that this is also an infinitesimal quantity, that is to say a very small elongation. This is only the elongation of the portion of the beam between x and x plus dx. Since this beam is already has a very small width, then the elongation will also be a very small quantity. So in this case, so the black part is before the deformation of the beam, and the red section is the same beam but after deformation. Okay, so let's see what we can do. So here now, because we have defined a very small portion of the beam, we can assume that everything is going to be constant, including the cross section of the beam. So what we can do is that we can calculate now the normal stress within the beam. Why? Because if we have the load, then we know that the normal stress sigma of x can be expressed as the ratio of the load divided by the area of the cross section. And if we define this width dx to be very small, then we can consider that the cross section will be roughly constant between x and x plus dx. So we can just use the cross section at x, since this cross section is going to be constant. So now that we have the normal stress, we can also express the normal strain, the actual deformation of the beam. So the normal strain here, it's going to be, so we are going to write it epsilon of x. That's going to be the normal strain at x. And for this, we are going to use the usual definition of the normal strain. That is to say, the elongation divided by the initial length. But we are going to write this only for this small portion of the beam. So we are going to use the usual deformation. So either we can write that this normal strain is the elongation divided by the initial length, or we can say it's the new length minus the old length divided by the old length. So in this case, the deformation of this beam is d delta. That's the elongation of the beam. That's the new length minus the old length. And we need to divide by the initial length. And in this case, the initial length of this small portion of this beam is dx. That's the distance between x and x plus dx. So that gives us the normal strain. So now that we have the normal strain, we can apply the Hooke's law. Why can we apply the Hooke's law? Because if we take a very small portion of the beam, with dx being very small, then we can assume that the Young's modulus is also going to be constant. It's not going to vary between x and x plus dx if we choose dx to be very small. So we can apply the Hooke's law. So the Hooke's law tells us that the normal stress is equal to the product of the Young's modulus times the normal strain. So this tells us that the normal stress is proportional to the normal strain with a proportionality constant that is the Young's modulus. And this is what we are going to use now to relate the elongation to the internal load that is subjected within this beam. So now we have the Hooke's law that relates the normal strain to the normal stress, and we have also some expression for the normal stress and the normal strain. So now we can replace the normal stress and normal strain by their expression that's going to give us a relationship between the load, P of x, and the deformation. So let's do that. So if we replace sigma, so sigma is the internal load divided by the area of the cross-section at x. Then we have the Young's modulus, and then so we have the normal strain, which is the ratio of the small elongation between x and x plus dx divided by the initial length of this beam, which is dx for this small portion of this beam. So we can rewrite this as follow. What we want to find is the elongation. So we are going to isolate the elongation d delta, and we are going to put everything else on the other side. So the elongation d delta is going to be equal to the ratio of the load. So we have the load first. So we have the internal load divided by the Young's modulus divided by the area of the cross section times dx. So now we have this relationship that gives us a relationship between the elongation on the left and the load on the right. So now how do we solve this? This is an equation that we can solve by doing a member by member integration. Why can we do that? Because here, so we have a relationship where on one side, on the left side, we have this member that only depends on delta. It only depends on the elongation. And on the right side, we have some terms that only depend on x. So because we have the right side that only depends on x and the left side that only depends on delta, then it means that we can do a member by member integration. So we can integrate both the left part and the right part while assuming that we integrate within the same limits. So what we are going to do is, in both cases, we are going to integrate between A and B, where A and B are the two extremities of this beam. We are going to integrate this small elongation over the entire length of the beam. So what we do is that we cut the beam into small section of length dx. We calculate the small elongation of this small portion of the beam between x and x plus dx, and then we sum all the elongation of all those small portion of all those small beams going from x to dx. We sum them all over the entire length of the beam, so that at the end, when we sum all those small elongation, then we will get the total elongation of the beam. And for this, if we do this, then we need to integrate both sides of this equation between the same limits a and b. That is to say, to integrate them over the entire length of the beam. So if we do this, what do we get? So first, if we integrate the elongation, the infinitesimal elongation between A and B, what we will get is the total elongation. So we will get the total elongation between A and B of the beam. And then on the right side, so we have this term, which is the integral between A and B of the ratio of the load divided by Young's modulus divided by cross-section times dx. So this, in this case, we cannot go any further, because after that, the value of this integral will depend on the actual evolution of the load of the cross-section area and of the Young's modulus as a function of x. So here, this is a very general equation, and we cannot solve it more than that without knowing the specific evolution of load, cross-section, and Young's modulus as a function of x. But in practice, this is the equation that we will be using to calculate the elongation. It's a general equation that will work for any situation. So in this case, in this equation, we have on the left, so we have the elongation between A and B. So this is the elongation of the beam in this case, but it doesn't have to be necessarily the elongation of the beam. This is the elongation between 2 points of the beam, so we can use this elongation between any pairs of points within this beam, not necessarily the two extremities of this beam. Then on the right here, so we have the internal load at x, so we need to express the internal load at each point x. We have also the area of the cross section of the beam, which also depend on x. And then we have here the Young's modulus. So the Young's modulus of the beam, which depends on which material this beam is made of. So if we look at all those terms can potentially depend on x. So if we look at the internal load can depend on x. It depends on where the external load are applied. So the internal load depends on the external load, but it can depend on x potentially. Then we have the area of the cross section. So the area of the cross section can also depend on x. This depends on the geometry. The internal load depends on the external load. You can get the internal load by using the method of section. So based on the method of section, you can use the external load to calculate the internal load as a function of x. The area of the cross section also depends on x, but it just depends on the geometry of the beam. And then you have the Young's modulus. It can also potentially depend on x, and this depends on the material that the beam is made of. If the material is not homogeneous, then potentially this Young's modulus can also depend on x. So in practice, to calculate the elongation of the beam, we will need to first determine the internal load at each x, and then once you know this, and once you know both the cross section and the Young's modulus, then you will be able to calculate the elongation by solving this integral. There is one case that is that does not always work, but there is that can work in a simplified case, or a special case, which again is not always valid, but in certain special cases. In the special cases where we have the cross-section area, the Young's modulus, and the internal load that do not depend on x. So if we have all those three, the internal load, the cross-section area, and the Young's modulus, if they do not depend on x, so if those quantities are constant and do not depend on x, they are homogeneous, do not depend on the position x. So this is a special case. This is not always true. Then in this case, the quantity p, e, and a, since they are constant, we can take them out of the integral. They do not depend on the position x. So we can write that the elongation between a and b is going to be equal to p, which we can take out of the integral, divided by ea, and then we are left with only the integral between a and b of dx. And in the integral between a and b of dx, dx is the small length of the cross section that we isolated. So if we sum all those portions of the beam of sum of length dx, if we sum them all, then we will get the total length of the beam. So this term is going to be equal to the length of the beam, the length between a and b of the beam. So altogether, in this special case, again, this is not always valid, but in this special case, the elongation of the beam between A and B is going to be the product of the internal load times the initial length of the beam divided by the product of Young's modulus times cross section. So in this case, you will have a simplified expression for which you would not need to explicitly integrate the load or the Young's modulus or the cross section. But again, remember that this is only valid when cross section, Young's modulus, and load do not depend on x. If one of those three quantities depend on x, then you will need to explicitly solve this integral. So as usual, it's useful to look at the units to make sure that the equation, the units make sense in this equation. So in this case, you have the elongation between A and B. That's an elongation. This is a change in length, so it's going to be in meter. Then you have the load, the internal load, that's in Newton. You have the length, that's in meter. Then you have the Young's modulus, so that's a stiffness. It has the same unit as a stress, so it's Newton per square meter. And then you have the area of the cross section. That's an area, it's in square meter. So if you look at those units, you find that both the right side and the left side of this equation, both the right and left member of this equation, are in meters, so the units are consistent. The other thing that you can look is whether this equation makes sense physically speaking, so we can interpret this equation. So what we find is that when we look at the elongation is proportional to the internal load. So the higher is the internal load, the higher the elongation will be, which makes sense. If you increase the internal load, then the elongation of the beam should increase. Then what we also find is that the elongation is also proportional to the initial length of this beam, which again makes sense because if the beam is longer to begin with, then its elongation is also going to be longer. Remember that what matters is not necessarily the absolute elongation, but more the relative elongation. So if the beam is longer to begin with, if it has a higher initial length LAB, then the elongation delta AB will also be longer, which in this case makes sense that the elongation is proportional to the initial length of the beam. Then what we find is that the proportional, on the other hand, is inversely proportional to the stiffness of the beam, inversely proportional to the Young's modulus, which again makes sense. If you have a beam that is very stiff with a very high Young's modulus, then the elongation should become smaller. So elongation should indeed be inversely proportional to the Young's modulus. And then the last thing is that the elongation is inversely proportional to the area of the cross section, which again makes sense. If you have a very thick beam with a very large cross section, then it should be more difficult to elongate this beam, which means that in this case, the elongation should indeed be inversely proportional to the area of the cross section. So if you happen to forget this formula, it's easy to find this formula either by thinking intuitively about what should be the effect of load, length, area of the cross section, and Young's modulus on the elongation, should it be proportional or inversely proportional, or you can find this formula by simply looking at the units of this formula and make sure that the right part and the left part of this formula have the same unit. So here to summarize, when you face an actual load problem and when you want to calculate the elongation, you will need to first calculate the internal load using the method of section, and then you will need to decide and to figure out, is the internal load, the Young's modulus, and the area of the cross-section constant, or at least constant over a certain region of the beam. If it's constant, then you can calculate the elongation using the simplified formula at the bottom. But if it's not constant, if the load is explicitly depending on x, or if the Young's modulus is explicitly depending on x, or if the area of the cross-section is also changing as a function of x, then you will need to come back to this equation at the top and to actually explicitly solve this integral to calculate the elongation of the beam.